Good morning, everyone. We will continue with the problem from last time. I want to finish this, and during office hours, I came to realize that maybe there are some issues or questions in dynamics that I may have to clarify. So I want to solve one more problem which kind of goes with what we're doing right now, but then dynamics is a little more scary. So I think if we understand that problem very well, then everything should be fine. Okay? Let me complete this problem first. Can everybody hear me? People in the back? All right, everywhere? All right, thank you there too. Okay, so here is the problem that we had from last time. This was the disk of mass M. Okay, this is rolling without slip. And this was attached to a bar of mass M as well. Okay. The center of mass of the bar is the point A. The center of mass of the disk is the point G. We wanted to obtain the equations of motion for the system. Because of the fact that the disk is rolling without slip, there is only one variable that describes its motion, which is theta of t. And because of the fact that this bar is fixed at the point O and performing circular motion, the center of mass of the bar is performing circular motion about the point O here. There's only one coordinate that is required to specify the motion of the bar, which we call as phi of t. Okay? So ACB this variable is theta of t, and then phi of t was the degree of freedom associated with this. Then we went through a host of kinematics. We were able to obtain the displacements of individual points on this body, okay, on these bodies. There are two of them here. I'm going to write the displacements very quickly. Okay, so delta of E is the displacement of the point E as a function of the angle phi. 2L phi of t from ACB. deflection of point A, delta A, L times phi of t, L being the radius of the circular arc which is traversed by the point A, about the point O. 2L being the radius of the circular trajectory that is traversed by the point E, about the point O. Keeping in mind that all of these are performing very small motion. Okay? We are looking at small oscillatory motion. Alright? Then likewise, deflection of the point B, because of the fact that this is rolling without slippage, 2r theta. And the deflection of the point D, which is attached to the disk at a height of r by 2. Is moving forward, or it is stretching depending on the direction of positive theta. If theta is clockwise positive, then the point D for a positive theta is going to move forward. It's going to stretch the damping element. Okay, so I had delta of D as r by 2 theta. Then we put together the free body and the kinetic diagrams. If I look at the spring, which is attached to the points A, the point B, the point A, the point B, the deflections. This is SCP. This is the undeflected position of the spring. Upon deflection and under the assumption that I have positive phi and positive theta, for positive phi and positive theta, if this is the case, and for L phi greater than 2r theta, if the deflection of point A is larger than that of point B, then what's happening to the spring? It is getting stretched. And we are drawing a free body diagram under this premise. Things are going to change because theta is going to keep getting positive and negative. I can't control that. I'm showing you a situation at some point in time. If we are consistent with what we have chosen as our SCP and so on, then that will automatically take care of theta being negative and the spring getting compressed. Okay? And for this situation, the spring is in tension. Okay, then we drew the position of the spring. Or L phi of t. This is the stretched length of the spring. We calculated all these. I'm not going to do it again. Stretched length of the spring. Unstretched length of the spring we said at L naught. And the net deflection of the spring is being stretched. So the forces Fs and Fs is k times the net deflection. Always the net deflection. Okay, it's not as if this force here is k times 2r theta and then this force here is k times L times phi of t. That's wrong. Right? It has to be the net deflection. Okay, because the spring is moving as an entity. And we are assuming that the spring is having very negligible inertia. So it has to be in a state of static equilibrium. Fs is the same on both sides. Okay? So Fs likewise, we did something similar for the damping elements as well. Let me maybe quickly draw them out. This is for the damping element C1 and the damping element C2. And if if I look at the situation, I'm going to see that both of them are getting stretched. Be careful. Both of them are getting stretched because of the displacement of respective points. That's D2. That's D2. That's D1. FD1, the left sides of both these damping elements are attached to the wall, so their deflection or their velocity at that end is 0. Okay? The velocity at the other ends will be whatever is the rate of change of the deflection of those ends. Okay? So this is going to be C2 times the following. Okay? And this one here is going to be C1 R by 2 theta dot. This is phi dot. This is the point B. And point D. Okay, these were the things that we had from before. Then I do the free body diagram of the disk and then that of the bar as well. And we did not have time to write out the equations of motion for the bar. And I have a few things to say about that creature as well, so I'm going to do that here. So for the bar, we already did the disk, so I'm going to skip that step. So I'm going to focus on the bar. Okay. Free body diagram. I'm going to have pin reactions. I'm going to draw the bar at some deflected position, okay, at some time t. So this is rho y. OX. I'm going to have the weight of the bar acting at the center of mass. mg. For the spring force, there are two ways that I can do this. I can either draw the spring force perpendicular to the length of the bar for very, very small motions, or I can draw it horizontal and say that the angle theta is very small. Let me do the latter. Fs, okay. Then I'm going to have Fd2, likewise. I have the length L and L, so this is L. This is also length L. I have the angles and so on. Let me very quickly sketch that out. Vertical position of the bar was SAP, right? And from there is phi, I'm sorry. This is phi of t, and then the distances that I have. So this is going to be phi, and L times cosine phi, L times cosine phi. For very small phi of t, cosine phi is approximately equal to 1. Okay? Okay. Then I had a torque which was acting on this bar which I did not draw in my initial figure, so let me draw that. Some T of t. This was an applied torque. Okay, so on the free body diagram, I have to draw all the external forces that are applied. I have to draw all the internal constraint forces, which is your pin reactions and so on. And then I have to draw all the forces due to the elements, which is the spring and the damping elements. Okay? So I'm going to have the torque. And that is essentially the free body diagram of the bar. I think I'm not missing anything else. Then I draw the kinetic diagram. This is depending on who teaches you dynamics, depending on the school of thought in dynamics. Some people draw the kinetic diagram, some people don't. I belong to the school where we draw the kinetic diagram because in my mind I want to keep things separate. It kind of lessens the complications when I think of the directions of the angles or the accelerations and so on. But it is completely up to you as long as you know what you're doing. I will follow the idea of drawing the kinetic diagram. What are the elements of a kinetic diagram? The following. First things first, the point A, as we suggested last time, is performing circular motion, so it's going to have a tangential and a normal acceleration component. The first two things on the kinetic diagram will be the mass times the accelerations in the respective directions. These are your inertial forces. Okay? So in this situation I have the following. Performing circular motions along the tangential direction. Mass of the bar times A suffix T. This is point A. This is point O. Okay? Then mass of the bar times in the normal direction. A suffix T and A suffix N, we looked at it last time. Please be careful, the tangential acceleration, if the length from point O to point A is a fixed length, is going to be the radius from A to O times theta double dot or phi double dot, whichever is the state variable that is in question here. We are going to talk about state variables in the next few lectures. Okay, so for the time being, please bear with me. An is likewise phi dot square. This is for a fixed radius. What's the radius that is in question here? This is the length from the point where the fixed center is to the point where the particle of motion is observed, which is the point A. This is the helipause. Okay? And I can mark it here as well. The last element of a kinetic diagram, if it is a rigid body, is called the inertial torque. The inertial torque is Ig, which is the mass moment of inertia about the center of mass, no other point. I'm not interested in the point O, I'm not interested in the point E or whatnot. I'm interested only in the center of mass motion. Ig times alpha is the resistance that the body portrays to any kind of a rotation. And that's called the inertial torque, as you know. Okay? It is drawn in the same coordinate convention that you followed for phi of t, and this is going to be in our situation Ia, because A is the center of mass, phi double dot. Do not draw it at any other point. There is another school of thought in dynamics that, okay, rather than draw the kinetic diagram, if I am summing up moments, then on the right hand side of the sum of the moments equation, I will just compute the moment of inertia about the point that I am summing it apart, which in this situation would be the point O, because I want the equations of motion. That is the utilization of the parallel axis theorem, which is seldom taught properly. And I avoid that particular idea, but you are welcome to use it. It will give you the same answer, it has to give you the same answer. But when you do that, you will not be showing any of these pictures if you are using the parallel axis theorem. You will be only calling it as I naught times alpha or I naught times phi alpha, depending on which point you are summing moment about. Okay? Alright. Are there any questions, please, before I proceed with my next train of thought? Yes, yes.
And the second damper, is that supposed to be D? Like point D?
This is supposed to be point E here.
Or sorry, I meant in like the second damper.
Oh, this is, yes, yes, you're right, yeah, that's my mistake. Sorry, thank you for pointing out that. This is point D, absolutely. Thank you. Okay, moving on. I'm going to leave this as a thought exercise for you, but I'll just write out the details. The equation of motion for the bar. Always remember, equations of motion should not contain the constraint forces, or it should not contain any of the constraints of the problem. This is because when I start solving for the problem, I don't know what the constraints are, the magnitude of the constraints to begin with. I have to actually solve the differential equation of the motion, obtain the displacement of the points of interest, which is the center of mass of any other thing, and then I have to find the constraint force. One of the greatest disadvantages of Newtonian mechanics is you have to deal, unfortunately, with constraint forces. But we live with what we have, right? Sum of moments about the point O on the free body diagram is equal to sum of moments about the point O on the kinetic diagram, counterclockwise, positive. Sketch out a few more things and then we go to the next one. Moments about point O, Fs times the distance of L times cosine phi in the counterclockwise direction. Fd2 times the distance of 2L times cosine phi, counterclockwise. What else do I have? I have the torque. Pride of place goes to the inertial torque, so put that creature first. Weight of the bar, don't forget that fellow. The weight of the bar actually produces an inertial torque or a reaction torque that will bring the bar back to where it wants to be. But the torque applied is trying to pull the bar back away from where it wants to be. The springs and dampers also will do that. Yes, yes, the question.
Should the applied torque be negative?
Yes, you are. Yes, you are. Thank you. Thank you. Mg times into the board, right? So this is going to be minus mg times the distance of L sine phi. That's all I have on the free body diagram. Okay? Then I go to events taking place in the kinetic diagram. It's a happening place. First thing I have is IA times phi double dot. Put it in the sense that you see it, it's clockwise. So minus IA times phi double dot. Then I'm going to have m times a suffix t times the distance of L. That's a force. Force times distance is a moment. Clockwise rotation. Or I can club them together, get rid of the negative sign. And this creature that you see on the right hand side is what many others should be writing as I naught times tan. So you can either write it this way, which is my preferred way of writing things, separating out the inertial torque, separating out the effects of the inertial force, which causes an inertial torque as well, or you can say, okay, by parallel axis theorem, this is the same as that. It's up to you. They should not give you two different answers. Is this point clear to everybody? This is of course a negative sign here because of the fact that there is a negative sign there. Okay. Alright, and the rest of them are details, but here is what you can do. Small phi cosine phi is approximately equal to 1. Sin phi approximately equal to phi. You can do the substitutions. This will become equal to 1, which is approximately saying that this spring force that I have drawn in the horizontal direction can be treated as a creature that is perpendicular to the length of the bar for small phi. Okay? And likewise for the damping force as well. And mg sin phi becomes mg phi. 2L cosine phi becomes 2 times L. Let me fill it out one more step, then move move on. Minus T L phi 2r theta times K times L, because cosine phi is 1. Okay, please note that. Then I have the damping force plus C times 2L phi dot, this is C2. Okay, and then I'm going to have the length, which is 2 times L times cosine phi, but cosine phi is approximately equal to 1 for small oscillations, so this becomes equal to 2. Gravity, my good friend, mg L times phi. Put everything together on the right hand side. It's minus 1/12. Watch out, it's 2L whole square because I'm looking at the total length of the bar when I'm doing the mass moment of inertia. Then I have the other fellow added down there, m times at times. Write out the equation of motion. Okay. After combining everything together, taking the negative signs out of the play and all these kinds of things, you'll end up with the equation of motion. I have half a mind to just leave it like this here so that you can complete it. Is it okay with everybody? Okay, we'll move on to the next problem. Okay? Alright. Next problem is a much more interesting creature. Obtain the equation of motion of a springy pendulum. What is a springy pendulum? It's just a yo-yo with an extensible spring. And it's performing oscillatory motion, but it's also performing motion in the radial direction. So this is a system that's going to have 2 degrees of freedom with gravity acting on it and many other things going on. There is a system. Mass of the bob is m. Stiffness is k. Okay, let me call the unstretched length as L now. Pivot is point O. This is the point A. Example for a springy pendulum, something that really comes to mind is you might have seen people sitting on these nice large baskets which is hung to the wall by means of a cable. They'll keep oscillating back and forth. You can do that once you're retired. Okay. It will also spin. I'm not looking at the torque. I'm not looking at motions that cause a torque on the pendulum bob because I'm assuming the pendulum bob to be a particle and the motion is restricted to the plane of the particle. It's a slightly simpler problem. Nevertheless quite complicated because there are 2 degrees of freedom. What are the 2 degrees of freedom? If I fix this to be in a position like this, I can take this pendulum bob and then move it up and down. That's 1 degree of freedom. If I fix the length of the pendulum, I can take this entire thing and keep oscillating it back and forth. That's another degree of freedom. So there are 2 degrees or 2 variables that I need to describe the entire dynamics of this problem, of this particle. Okay? So 2 degree of freedom system. Gravity is present in the problem. Okay? So we need to know how to handle this. This problem is different from the following. Let me draw it out here. simpler version of the problem, which I'm not going to do anything about in this question.
So our TA was teaching us how to find the number of degrees of freedom. So with the coordinates, it would be free because the particle on a plane, and then is the only constraint of the spring once it stay on.
Very nice question, very nice question. So if you really want to go into the details of this, here is the idea. You're absolutely right. You have to start off by saying that this is a particle in 3D space. So it's going to have how many variables that describe its position at any point in time? 3, right? X, Y, and Z. The constraint is that it is performing planar motion. The presence of the spring is not a constraint. For all practical purposes, the spring is not a constraint. If it was a spring, it would be a constraint. Okay, so let me maybe write this up. That's a good point. Let's see. So they are typically called as configuration coordinates. Okay, so configuration coordinates. That is the number of variables that you need to describe the motion of point A in the absence of constraints. Without considering anything about constraints. This is a particle in 3-dimensional space. I'm going to have 3 variables. What are the constraints for this problem? Motion is restricted to a plane. Planar motion, which means that the z distance, if you assume the z to be the distance out of the plane, the z distance is a constant. Okay? So z is equal to z naught, essentially. Which means the number of degrees of freedom is the difference between the number of configuration coordinates and the number of constraints, which is 3 minus 1, so degrees of freedom are 2. But you've got to be careful. The degrees of freedom are 2 independent variables. And there are multiple choices for a degree of freedom for a body. In this problem, you can very well say that x and y could be degrees of freedom, but x and y will be related by means of an angle theta at any point in time due to geometry. So it would be better to say that theta, which is the angular location of the mass, and some radial distance along the length of the spring at any instant in time, these are your degrees of freedom. Okay? The choice of a degree of freedom is not very obvious in most problems. It's an issue. For most problems that we solve, the degree of freedom is very obvious. You're looking at something moving horizontally or vertically, or something performing oscillated motion. Okay? All right. What I wanted to tell is that this problem is not the same as the following problem. We solved a problem of this nature. In the problem that we solved a couple of lectures back, there was a damping element as well attached to the ball. How many degrees of freedom? It is constrained to move only vertically. It is constrained to be in the plane of motion. Between 2 constraints, 3 configuration coordinates, so the number of degrees of freedom is 3 minus 2, 1, which is just vertical motion, up and down. What was also true for us the last time we derived the equation of motion of such a thing? Can somebody tell me? Yes? Started at SEP, so we ignored that. Fantastic. The question in my mind is, can I do the same scheming thing for this problem here? Can I start at SEP and say, okay, gravity goes to hell? Can I do that? Yes, yes.
No, because the spring force won't always act opposite to gravity.
The spring force is going to be radial, right? But there is a certain static deflection that I start off with. And that static deflection of the spring is going to balance the force of gravity, correct? So the question in my mind is, can I say, okay, gravity is gone? What is the function of gravity in this problem? I have a pendulum, I swing it, what's the function of gravity? It brings it back by exerting an inertial torque, right? So in relative respect, this problem is a simpler version of the problem, and you will see why we cannot ignore the force of gravity. I'm still going to start the problem from SAP, and you will see what's going to happen. Okay, so let's do this. Let me maybe take that panel there. I'm going to draw three figures. First figure is when nothing is attached to the spring. Okay. At this point in time, because the spring is massless, its unstretched length is the situation that you see here. This is the creature diagram. Then I come and I slowly attach this mass M to the end of the spring without giving it any kind of an external input. Okay, I'm not applying a force, I'm not applying any initial conditions. I just come, place it gently underneath the spring. What happens? The spring is going to stretch by a very small amount, right? This is your delta static. That is actually the static equilibrium position. So this is the SEP for the problem. At the static equilibrium position, if I draw the free body diagram, spring is stretched by an amount delta static, so it's going to exert a restoring force back on the mass. These two are going to balance each other out. K times delta static, or delta static is mg divided by k. So far so good. This is pretty much the same as how we dealt with the problem like that, the simpler version of the problem. Now from the SCP, I'm going to give this problem some initial conditions. We have not discussed initial conditions yet, but essentially I'm just going to give this guy a good kick, which means I'm going to give it a certain displacement in the angular direction, or a velocity in the angular direction, or perhaps a displacement in velocity along the length of the spring. Okay? So I'm going to draw its position at some random point in time t. Spring is getting stretched. This is SEP. And I'm going to assume positive coordinates for theta. Theta of t is positive if it is counterclockwise. It's just my assumption. And from SEP, I'm going to assume that the displacement of the spring from the static equilibrium position, which is R of t, from SEP is positive in the manner shown. Okay? Now, I want to draw the free body diagram of this spring. At SEP, what is the length of the spring? L naught delta static, correct? place, assuming that the spring is stretched. If it is stretched this way, it is positive R of t. If it is stretched the other way, it is negative R of t. Assuming a positive sense for R of t, or a positive coordinate direction for R of t. What is the total length of the spring? Is going to be the static length at equilibrium position plus the displacement R of t. L naught delta static plus R of t. Does this make sense to everybody? So what's the deflection of this line? I'm just going to call it as delta R. This is the stretched length minus the unstretched length. What is the stretched length? It is this meter here. So this is L naught delta static R of t subtracted from the unstretched length of the spring. What is the unstretched length? It is going to be the length L naught before the static equilibrium position. It's not L naught plus delta static minus L naught. And the spring deflection is now calculated here. So Fs is k times delta R. For a positive R of t, the spring is getting stretched. Right, now I'm ready to draw my free body and kinetic diagrams. I'm going to draw them from the static equilibrium position. Gravity is still a factor in my problem because I'm still including the static stretch of the spring. Okay, we're going to look at small motions. So theta of t is small, R of t is also small. Okay. Free body diagram. That's an arbitrary theta. This is the mass, spring force, Fs, maybe spring first. For R of t greater than 0, spring is getting stretched. Then I draw the particle. Fs is pointing equal and opposite. Those are the points where the mass was attached to the spring. So the spring force is equal and opposite, as you can see. Weight of the body is acting vertically down. Mg. This is a free body diagram. I have the kinetic diagram. What's in the kinetic diagram? Mass times acceleration in the tangential direction, mass times acceleration in the normal direction, depending on how we describe it. Let's say that this is performing motion along a path of variable radius. You see, this is now performing motion in the polar coordinate frame, in some sense. The distance r from where the point O is to where the particle is no longer a constant radius. So I cannot necessarily say that the tangential acceleration is some radius times theta double dot. That's completely wrong. It's a little more trickier than that now. mass times acceleration in the tangential direction. I'm just going to draw it out, mass times acceleration in the normal direction. I'm going to keep this figure here, okay? Or if you want, you can also choose a polar coordinate frame, mass times acceleration in the theta direction, mass times acceleration in the radial direction. What's my radial direction here? Is this way. This is the radial unit vector. The transverse unit vector is E theta, perpendicular to ER. And if you choose a coordinate frame of this nature, then my direction of the acceleration is drawn on the kinetic diagram will reverse. Mass times acceleration in the radial direction, which is nothing but the opposite of what is the normal direction, and this is the same as mass times acceleration in the transverse direction, as you would recall from dynamics. And you would further recall from dynamics the entire expression for the tangent, transverse, and the radial accelerations. Okay? For a variable radius, let me call it as y, if it is a purely circular motion, this is the only acceleration I'll be seeing, y times theta dot square in the normal direction. This is not a purely circular motion taking place. A theta is, I'm sorry, this is, I have to switch it up. This is a theta, sorry. And I have AR is 2 times y dot. Sorry for that, I'm still fine. This is AR, this is a theta. It's 2 times y dot, theta dot, which is your Coriolis acceleration term, okay? Plus y theta double dot. That's your tangential acceleration or your radial acceleration. Tangential to this pure circular motion. You will have only y times theta double dot. If it is pure circular motion, you will have only y times theta dot square. What is y in our problem is the total length of this spring or the total distance of the point A from the curve, or the total distance of the bob from the curve. Okay, so for us, y is del naught, delta static, and R of t. Does this make sense to everybody? And if not, let me very quickly depict this in a figure. Point A, point O. I don't know what kind of a trajectory that point A, which is the mass location taking place, is performing. I don't know really. It's an arbitrary path. At any point in time, I'm going to have my radial unit vector ER pointing this way. My transverse, if I'm assuming a polar coordinate frame, I can assume a normal tangential frame as well, where the unit vectors are changing directions as I travel along the path. It's absolutely fine. No harm done. Okay? E theta. the radius of this path is changing over time, or the length is changing over time. So this is y of t. And then theta of t is from some kind of a fixed vertical. And the accelerations are what you would have seen from your undergraduate dynamics course. Y double dot minus y theta dot square. Y theta dot square is the acceleration if you are performing circular motion pointing in the normal direction. Then I'm going to have the tangential acceleration, Coriolis acceleration, which you have seen in rigid bodies, but it's really coming from the particle itself. Okay? All of these put together is the net acceleration for my problem, and my free body diagram has vanished somewhere. It's perhaps present inside here. Okay, so that's my free body diagram and my kinetic diagram. What I want you to do as an in-class quiz is by Friday, this is your second in-class quiz, by Friday I would like you to obtain the equations of motion for this springy pendulum, assuming small motion. Okay? So obtain by Friday for small theta, which means sin theta is theta, cos theta is 1 for small theta. Obtaining the equation of motion by Friday, 12:40 p.m. I have created an online Dropbox, and I will for sure have the solutions of this posted, my own work posted on Current. Okay? And I also wanted to spend time talking about the rate of change of unit vectors and so on as a function of time, as particles travel along a path or a rigid body travels along a path. I know you may have come across this in dynamics as well, but I will probably spend time doing that on Friday. And then we'll move on to torsional springs and torsional dampers. It's slightly more different in nature, but they perform the same act, they perform the same duty, in that if a body is trying to do something, these will produce a restoring torque, no longer a force, you see. Alright, thank you all.
Mm-hmm.